All right, time to move on and delay anymore. This next presentation is about derived quantities. So as we said many times, this is really what SPICE is for. So that's the data that you want to be computed. The parameters you want to be computed based on SPICE kernels, and this is the primary reason for SPICE toolkit. Well, again, SPICE toolkit contains many routines that assist you with these kind of computations. Some are fairly low level, but some are quite high level. And we keep adding them, not at any particular case, but as we feel the need in certain interfaces arises and becomes more prominent. So in all cases, of course, you need to get all the data, and then you call SPICE toolkit APIs from within your program, and you get all kinds of things out, such as altitudes, phase angles, latitude, longitudes, so subspace captain, subsolid points, and such. So the examples will follow in several pages. Again, to repeat, there are two kinds of computations in SPICE, computing geometric parameters or conditions at a given time, or doing the inverse of that, finding times or time spans when specified event or specified geometric condition exists, the geometry finder APIs. This is a very large topic, and there's a separate tutorial on geometry finder. I believe we have presented it already, but there is a longer version of it on our website, and we recommend you to look at that. So let's first look at some examples of geometric parameters. We have a few routines that compute illumination angles, phase, incidence, and emission that are important in processing of all kinds of remote sensing data. These routines all begin with illum for illumination, and they have a letter at the end indicating the kind of illumination computation that is done. illumF, for example, computes illumination angles with flags that indicate if the point for which these angles are computed had been visible from the observer and it had been illuminated by the sun. illumG computes illumination angles for general illumination source, not just for the sun. And the original routine illumine computes illumination from the sun. There are two routines that compute subpoints, sub-solar point and sub-observer point, sub-SLR and sub-PNT. There is a number of routines that compute surface intercept points for a given ray on a given target as seen by an observer. And they can do it using the core routine called SynSept can do it for both ellipsoids and DSK-shaped targets. But there are two special routines that are faster. They can do it just for DSKs, DSK-XD and DSK-XSI. This one simply computes intercept points, but this one also returns the data about file and segment from which were the plate based on which the computation was done. There is a routine that computes longitude of the sun, which is an indicator of seasons, LSPCM. That's frequently included in data labels. There is a routine that computes phase angle between body centers. There are a couple of routines that compute limb points and terminator points, as seen by a target on a body that's modeled as ellipsoid or DSK. A routine that computes surface points for specified latitude longitude grid, LabSurf, again for ellipsoidal body or for DSK. And there's a routine that computes surface normals at these points that are frequently computed by either SynSept or SurfPoint. This routine is called SurfNormal. As you can see, these are pretty cryptic names, but if you get used to abbreviations that we've been following, you can kind of get the gist and you can locate them pretty easily. There are a few routines that test for geometric conditions, a ray in the field of view, FOB ray, whether the ephemeris object is in the field of view, FOB target, and a routine that determines occultation condition, both occultation and transits, called a cult. On the geometry finder side, there are many routines, and this shows some examples of searches that you can do. For example, you can try to look for interval when rays in the field of view. This will be GF, field of view. GF is normal prefix for all geometry finder routines, followed by 4 letters indicating what the functionality is. This routine searches get field of view, GFT FOV, searches for times when an ephemeris object is within field of view. This is a routine that's called by WGC that you could see in yesterday's Marx example. There's a routine that checks for occultation conditions or transit for times when a certain occultation or transit condition is met, GF occult. When object is at periapsis, GF distance, GF dist. It could be also checking for apoapsis, or when the distance between two objects is greater or less certain value. There's a routine that checks for various coordinate conditions, for example, such as latitude, longitude, and specified range, GF plus C. Position coordinate, OC stands for position coordinate, and there is a routine that checks on conditions on illumination angles, being used in specified name in GF illum. There is far more functionality in GF available. You really need to look at the tutorial, which has many more examples of routines and uses, and the GF required reading. So we have lots of functions related to computing various geometry parameters for extended objects such as ellipsoids, planes, ellipses, and lines. The routines for computing nearest points on ellipsoid, is surface ray intercepts for ellipsoids, surface normals on ellipsoids, points on the surface, limb on ellipsoid, slicing ellipsoid with a plane to return an ellipse that results from it, of altitude of radius in the ellipsoid. These are lower level, more mathematical routine, and they require you to compute directions using SPK routines in order to, and have them in the same frame in order to call some of them, but majority of them provide examples which will get you going in their use. Routines that deal with plane is intersecting ray and a plane, with ellipses projecting ellipse into a plane, and finding semi-axis of an ellipse, and with lines, very important routine to find nearest point on the line or a segment. I'm not going to name all these APIs. It's important for you to remember that these functionality exists, and you can always look at this slide or the documentation provided in the HTML documentation set. As well already mentioned, we have lots of routines that transform between different coordinate systems. The one that's most flexible, XFM state, transform state, can take state vector between any coordinate system from any coordinate system to another coordinate system. This routine is very flexible, but it's not very fast. If you want faster transformations, you will use routines that deal with individual coordinate pairs, like latitudinal to and from rectangular, linear-graphic to rectangular, and from rectangular, and so on. Usually they have very clear pattern. You have the coordinate system from which you are converting, like latitudinal in this case, and to which you are converting, like rectangular, so you get a flat track name. As you can see, all these names are formed in the same way. We have quite a few vector routines that do dot product of vectors, cross product of vectors, that add vectors, subtract vectors, and so on. These are the names of these routines. The routines that are a little bit more sophisticated, that project one vector onto another vector, and there's a routine that can build a reference frame transformation based on two vectors. In fact, that routine is the basic concept of how two vector frames and dynamic frame subsystem are done. We'll present dynamic frames in the last day of this class. There are a few routines that deal with matrices, multiplying matrix by a vector, matrix by matrix, transpose of matrix by a vector. As you can see, the pattern of these names is pretty simple, m times matrix and so on. So again, you need to remember that some of these exist. Of course, for languages like MATLAB and IGL, this is not essential. They have built-in capabilities for that. But C, in general, does not, and so forth. So there's this family of routines that deals with converting between various representations of rotations, such as Euler angles and Euler angle rates, rotation and axis or quaternion, and matrices that are used to transform vectors. These routines are for Euler angle to matrix and from matrix. As you can see, it's Euler to M and M to Euler. So again, the name patterns are pretty clear once you get used to the abbreviations that we use. The transformation from rotation axis and angles is rotation axis angle, rotation to axis and angle, and axis and angle to rotation. And for quaternions, it's even simpler: Q to matrix, quaternion to matrix, and matrix to quaternion. And this is a SPI-style quaternion that you must have as input. And we have a white paper that we mentioned in one of the previous presentations that explains that. There's a set of Coordinate transformation routine for velocities. Again, the most flexible one is XFM state, which will take state in one of the coordinate systems and transform it to the other, both the position component of it and the velocity. But if you want to deal with individual transformations, which are faster, you can call one of these routines that transform velocity, that generate Jacobian transformation for the velocity. velocities. Here's an example of how it's done. If you have full vector return, for full vector transformation, you can compute a state using spiftp.esac.esa.int. It will return you a state of target with respect to observer. And then you can call XFM stop to transform this state from rectangular coordinates to spherical coordinates. And your output state in this case will contain, for spherical coordinates, the derivative of radius, call attitude, and longitude. A faster way to do it for velocity-only transformation requires you to first compute the Jacobian transformation and then multiply this velocity component of the state by this Jacobian. While there's a caution, the coordinate transformation often have singularities, so derivatives may not exist everywhere. These exceptions are described in the headers of the Jacobian routines, and usually they would signal errors if asked to perform an invalid transformation. So in the next several pages, we will present real-life examples of using some of these derived quantity APIs. You can see more of these examples in most used SPICE APIs, and of course the lessons will require you to do some of these computations. In fact, some of these slides map exactly to what you're asked to do in the lessons. So let's look at the first one. Given the direction of an instrument bore sight and a body fixed frame, return the illumination angles, incidence, phase, and emission at the bore sight, surface intercept of an object, with an object shape modeled by ellipsoid. So the angles are shown here. The emission angle is the angle between direction to the point and the normal to the surface at that point. The incidence is the angle between the normal to the surface and direction to the sun. And the phase is angle between direction to the point and direction to the sun. So here's these three angles indicated. And of course we have a target observer position vector indicating where our observer is with respect to the target. So that's pretty simple. First, we need to figure out what the bore sight vector is, and we'll use get field of view routine that we'll discuss in tutorial related to I-terminals later today. After we got bore sight vector, we can call surface intercept routine, syncept, to call intercept, to find intersection of bore sight direction with the surface, this point. And then, using that intersection point as input, we can compute the illumination angles at that point. So in three calls, you determine your interception point and illumination at that point. So let's look at something more interesting. Let's see how we determine intersection of the apparent line of sight between Earth and Cassini spacecraft with Saturn ring plane and determine the distance of this point from the center of Saturn. So we're looking for this point. We have an observation for radio occultation of the rings of the spacecraft by rings. We're interested which point the signal goes through and this distance, whether in which of the rings of Saturn we are. So let's see, in this computation we'll do it for reception case. The first thing we need to do is we need to get a lifetime corrected position of the spacecraft as seen from Earth at the time of interest in the inertial J2000 frame. And we do that by calling top-level SPK API, SPK-ECR. We're talking about this position. The second position we need is lifetime corrected position of the center of Saturn as seen from Earth, also in inertial frame. And this vector is not shown here. This would be the vector from the Earth to the center of Saturn. Then we need to compute rotation matrix that rotates from Saturn body fixed coordinates to the J2000 frame at the epoch corrected for lifetime. So we will compute this frame at the epoch, which is ephemeris time that we used as input to these two routines, minus the lifetime for Saturn center. The third column of this matrix gives direction of Saturn pole in the J2000 frame, and we'll call it Sat pole. Once we have this pole, knowing the location of the center of Saturn with respect to Earth, we can build a plane, a ring plane, a structure in SPICE using these two inputs and using this NBP to plane routine. Then we can call routine that intersects direction ray with a plane, and we will use the Earth spacecraft vector as the direction and the plane that was built by this call. And the intersection of this plane will be the intercept point that we're looking for. Once we have that point, we can compute the vector pointing from the center of Saturn to this point by simply subtracting the vector to the center of Saturn from the vector to this point. And then we can compute magnitude. We do it by the subroutine, and then we compute magnitude of that vector, which is the distance that we're looking for, using v norm. Well, of course, this is a simplified computation because it ignores the difference of light time to the center of Saturn and actually to the intercept point. So if you wanted to do more complicated computation that takes this into account, you can recompute position and orientation at Saturn at the light time from the Earth to the intercept point, which you have by scaling that vector that we obtained. And then you can take a loop to have this converge until your light time converges. So it seems pretty complicated, but with SPICE there is a hack for everything. Let's see how you do it in a hack way. Instead of trying to compute all these vectors, we're going to try to set up a dynamic frame which has one axis pointing from the Earth to the Cassini orbiter. We will have a big tutorial on the last day that talks about dynamic frames. So this dynamic frame will ensure that this direction is always a constant vector, for example, z-axis in that frame. Then we will temporarily change the radius of Saturn, the radii of Saturn, to be different from they actually are, making one of them really big. So our Saturn extends well beyond its ring, outer ring, and we make it very flat, like a pancake. So essentially squish it and make it into a plane. We can do that by either editing PCK file. It's a text file that you load into your program, or by using a routine that can simply switch Saturn radii within the full structure that buffers all the data from it. Once we have done it, we get this pancake Saturn over here. We can use surface intercept routine to find the intercept of the Earth's Cassini ray with this flat ellipsoid. In this case, because we're doing surface intercept, all light time directions will be done to that point, so it will find it very accurately. So once we have found this point, of course, we can use v norm to get the distance of the intercept from the Saturn center. And it would be good to restore original Saturn radii because we don't want to keep it as a pancake. We can do some real geometric computations later with it. So as you can see, this is sort of a hack, but it's a very simple hack, and it's implemented using the routines that do a lot of heavy-duty machinery related to light time corrections that you would otherwise have to write big loops and convergence loops for. And the final example is occultation events. Let's determine what spacecraft will be occulted by an object, such as natural satellite, as seen from an observer. So for that, we would use one of geometry finder routines, GF occult. We need to select start epoch and stop epoch and the step size. Well, start and stop epochs, of course, can bracket multiple occultation events. So we need to select the step size such that it should be smaller than the shortest occultation events that we expect, and smaller than the minimum interval between two occultation events that are to be distinguished. Well, let's take an example of Mars orbiter, one of NASA Mars orbiters, say Mars, either Mars 2001 or MRO. There are approximately 2-hour orbits. These orbits are oriented such that they always go behind Mars with respect to the Sun. Probably for a fraction of an orbit that's about 15 to 20 minutes long. So our step should be smaller than that fraction. So that's how you should think about this geometry situation. Of course, if you're flying around a tiny asteroid and your trajectory is not as simple, can be very well approximated by two-body motion, you cannot use this simple fraction criteria that I use. You have to use something complicated, but you need to really think about geometry situation to pick that step. So you're not running a search which would miss a lot of events. Once you have done that, you would insert this search interval into a SPICE window, the structure called window, or in this case it's going to be called confining window, and then you just call GF occult to find these occultations. And the time period within the confinement window over which the occultation will occur will be returned in another splice window. So GF-occult can treat targets as ellipsoids, DSK shapes, or points, but at least one must be ellipsoid or DSK shape, and DSK shapes can be combined only with point targets. And it can search for different occultation or transit geometries, full, partial, annular, or any.